What if I told you a computer can learn to recognize a cat without anyone ever explaining what a cat is? The first time an AI saw this picture, it confidently said, "Dog." This tiny digital brain started knowing absolutely nothing, but after seeing thousands of pictures, it became an expert. At the beginning, our little brain is nothing more than a computer program. Inside it lives a vast network of tiny units called neurons. Think of them like thousands of tiny light bulbs arranged in layers. At first, every bulb is dim, almost asleep. Each one simply holds a number. Nothing more. They don't think. They don't understand. They just wait for information. These neurons are organized into layers. An input layer where information enters. An output layer where answers come out. And in between, many mysterious hidden layers where the real magic happens. But neurons alone aren't enough. Every neuron in one layer connects to neurons in the next. Imagine thousands of strings connecting them. Some strings are thick. Some are thin. These strings are called weights. A thick string means, your signal matters a lot to me. A thin string means, your signal isn't very important. But at the start, these weights are completely random. The brain is a chaotic mess. A cat's whisker might accidentally connect strongly to the dog answer. The network has no idea what anything means yet. Now we show the little brain its very first image. A blurry picture of a cat. But computers don't see cats. They see numbers. Every pixel in the image becomes a number representing brightness and color. These numbers flow into the input layer. Some neurons glow bright. Others stay dim. The picture has officially entered the brain. Now the signals begin to move. Each glowing neuron sends its number forward. But before sending it, something interesting happens. The signal is multiplied by the weight of its connection. If a neuron glows with a value of 0.8, and its connection has a weight of 0.5, the signal arriving at the next neuron becomes 0.4. Every neuron receives hundreds of these signals. It adds them together. If the total becomes strong enough, the neuron fires. Then it sends its signal forward to the next layer. This cascade continues, layer after layer, through the hidden depths of the network. Thousands of tiny calculations happening silently. Finally, the signal reaches the output layer. Here we have two neurons. One represents cat. The other represents dog. Each one glows based on the signals it received. Whichever neuron glows brighter becomes the network's guess. And in this first attempt, the dog neuron shines brightly. The cat neuron barely glows. The network proudly announces, "It's a dog." But it's wrong. Very wrong. Luckily, the network has a teacher. For every image we show it, we also provide the correct answer. The label says, "This image is a cat." The perfect output should have been, dog 0%, cat 100%. But the network said the opposite. So now it must measure how bad its mistake was. To do this, the network uses something called a loss function. Think of it as a ruler. It measures the distance between the network's guess and the truth. In this case, the distance is huge. The network was very confident and very wrong. The loss function produces a single number, the loss score. And the network now has one mission: make that number smaller. So the network asks an important question. Which of my connections caused this mistake? To answer this, it works backwards through the network, starting from the output layer, moving back through every hidden layer. This process is called backpropagation. It calculates how much each connection contributed to the final error. Some connections clearly pushed the answer toward dog. Others failed to push it toward cat. Those connections must change. Now the network makes tiny adjustments. Connections that helped produce the wrong answer are weakened. Connections that should have helped produce the correct answer are strengthened. But the changes are very small. Just tiny nudges. Because learning too fast can cause chaos. This adjustment speed is controlled by something called the learning rate. Too high, and the network becomes unstable. Too low, and learning becomes painfully slow. So we move forward carefully, one tiny step at a time. The correction doesn't stop at the output layer. The error signal travels deeper. Even neurons buried deep inside the hidden layers receive feedback. They learn how their signals contributed to the mistake. And they adjust their own connections as well. Every weight in the entire network shifts slightly. Millions of tiny adjustments, all working toward one goal. Reduce the error. Now we show the network the same cat image again. But something has changed. The connections are slightly different. The signals flow through a new path. This time the network hesitates. Maybe it's a cat? The cat neuron glows a little brighter. The dog neuron becomes a little dimmer. The loss score shrinks. Still wrong. But it's less wrong. And that means progress. Of course, one image isn't enough. So we show the network thousands of pictures. Cats sitting. Cats sleeping. Cats in the dark. Dogs of every breed. Birds. Cars. Trees. For each image, the network repeats the same cycle. Guess. Measure the mistake. Send the error backward. Adjust the connections. Again. And again. And again. This process is called training. Slowly, something incredible begins to happen. The random chaos inside the network organizes itself. Neurons in the first layers learn to detect edges and lines. Neurons deeper inside combine those edges into shapes. Ears, eyes, whiskers. Even deeper layers begin recognizing entire faces. Without ever being programmed with rules, the network discovers the hidden patterns that define a cat. Now comes the real challenge. We show the network a picture it has never seen before. A completely new cat. Different lighting. Different angle. Different background. If the network only memorized its training images, it will fail. But if it truly learned the pattern, it will succeed. The image enters the network. Pixels flow into the input layer. Signals cascade through the neurons. Edge detectors fire. Shape detectors activate. The deeper layers recognize familiar patterns. The signal reaches the output layer. And suddenly, the cat neuron blazes with light. The network confidently announces, "It's a cat." And just like that, a brain that once knew nothing has learned.